If f is positive, continuous, and decreasing for x greater than or equal to 1, and if your a sub n, your nth term, you write it as a function of n, where n is the counting numbers, then the infinite series and the integral from 1 to infinity of that function that you let represent your nth term will either both converge or diverge. Confirm that the integral test can be applied to the series, then determine convergence or divergence. So our term, if we take a couple of n values, we notice that when n is 1, n is 2, n is 3, that we get always positive and decreasing values. Let's go back up here to the top. There's another one. We have positive, decreasing. As far as the continuous goes, what I look at, and I'm going to scroll back down, is the denominator is 3n plus 1. Now, if I were to let that be a function 2 over 3x plus 1, it would have a vertical asymptote at negative 1/3. But see, that's not going to be part of where we're investigating. So the third condition of continuous is also met. So what we're going to do is we're going to write this nth term as a function of x and integrate it from 1 to infinity. Well, first thing I want to do is, because the denominator's derivative is 3, not 2, is I'm going to pull that 2 out front. And then I have the integral from 1 to infinity of 1 over 3x plus 1. If our numerator is only off by a constant to have the derivative, you can multiply that in. Just remember to rebalance it. And again, that's from u substitution that we looked at the very first week of class. So that gives us 2/3, the natural log of absolute value of 3x plus 1. And we're going to look at what happens at infinity and at 1 and take the difference. Remember, we can replace infinity with the letter b. So what I'm going to do is I'm going to take the limit as b goes to infinity of ln 3b plus 1 minus, now we sub in the lower value, 3 times 1 plus 1, that's natural log of 4. Well, since this natural log, the larger this gets, the larger the natural log value gets. So that'll actually go to infinity, and because we don't have a finite value, that just tells us that the series diverges. The next example, we have the infinite series 1 to infinity of e to the negative n, which also think of that as 1 over e to the n. Over here to your far right, I'm going to look at this function 1 over e to the x. If you graph that, we have this curve here. Now notice that that graph is continuous, always positive because it's above the x-axis, and it's decreasing. So all three conditions for integral test are met. Integrating from 1 to infinity, e to the negative x, that's negative e to the negative x. We're going to investigate at infinity and at 1. So we're going to take the limit as b goes to infinity. Notice how I replaced the infinity with b, but I'm putting that limit in there. That's going to tell us we have the limit as b goes to infinity of 1 over e to the b. Now, I transferred that to the denominator. E to the negative x, you can move it to the denominator, and then the power becomes positive. Minus negative, that's why I have a plus sign. And then we sub a 1 in, 1 over e to the first. Well, this new fraction here, a fixed numerator and ever-growing denominator, that's going to have a limit of 0 plus 1 over e. That is a finite value, so that tells us that we have a convergent series. I do want to point out, and I mentioned it in class, if your limit has a finite value, that is not the sum of your series. It just tells us that the series will converge, and you'd have to use other means to find the sum. confirm that the integral test can be applied to the series, and then determine convergence or divergence. So same test, just switching up problems really. I like to do a lot of examples in class. Our denominator, it's never going to be 0, so that will always be a well-defined function. You can check with some n values that this does always stay positive, always decreases, or at least it decreases after a certain point. What I do in class, if you guys will remember, is I actually put this in my graphing calculator and graph it. If it's got a signature look of staying above the x-axis and heading downhill as it goes right, then all three of your conditions are met because a smooth graph is continuous. It doesn't have any asymptotes is what I'm trying to say. And it's always positive because it's above the x-axis, and decreasing because the slope is always negative. Converting this nth term to a function of x, integrating from 1 to infinity, our denominator has a derivative of 4x, which is exactly our numerator. That makes it a perfect antiderivative of natural log. So natural log of our denominator, absolute values. You can actually get away with parentheses because that's never negative or 0, but absolute values will cover you. I'm going to replace the infinity with the letter b, but I'm going to let it approach infinity. This was all back in our improper integrals section too. Natural logs, the larger this gets, the larger your natural log of that gets. So it goes to infinity. We have a divergent series. It actually doesn't matter what this is back here. It turns out it's just natural log of a fixed value. I mean, it really does matter, but infinity is going to override a constant. Our next series, we have the sum from 1 to infinity of 1 over n squared plus 1. N squared plus 1. Now, the larger n gets, the smaller these get. N squared plus 1 is never 0, so you don't have to worry about asymptotes. And that means it's continuous. So we have positive, decreasing, and continuous. We can use the integral test, 1 over x squared plus 1. This is a special fraction here. Its antiderivative is tangent inverse of x. Over here in purple, just as a reminder of what the graph of tangent inverse x or arctan of x looks like. The larger b gets, the closer you get to this horizontal asymptote of pi over 2. Arctan of 1 on the unit circle at pi over 4, you have a tangent value or y coordinate divided by x coordinate of 1. So arctan of 1 is pi over 4. This has a finite difference telling us that this series converges. It doesn't tell us what the sum is, it just tells us that it's convergent. The next part, we're going to look at what's called a p-series. It's an infinite series, but it has a special form, and we call it a p-series because you have progressively increasing values of counting numbers. It's actually your n values that increase with a fixed power, and we call that p. It turns out if your series can be written in this format and your power is greater than 1, then your series will converge. However, if this power is between 0 and 1, including 1, then it'll be divergent. For p to be exactly 1, where you'd have the sum from 1 to infinity of 1 over n, this is called a harmonic series. 1 plus half plus third plus fourth and so on. It is divergent. You can verify that with the integral test. This antiderivative is natural log of x. As x gets large, so does natural log of x, and so it will be divergent. Under here, we're going to have some examples where we look at certain patterns. We're going to try to develop a p-series from the pattern we see, and then we'll decide on what p-value we have and whether or not we have convergence. First example, 1 plus a fourth plus 1/9 plus 1/16, and so on. These are all perfect squares. This is understood to be over 1, so that's 1 squared, 2 squared, 3 squared, and so on. Progressively larger counting numbers, all squared. Our p-value is that power. That power is greater than 1, so this series converges. In our second example, we have, and you always think of 1 as 1 over 1 if you need to. So we have 2 square root of 2, 3 square root of 3 in the denominators. That's 2 to the first, 2 to the half, 3 to the first, 3 to the half. When you multiply like bases, you add their powers. 1 plus a half is 3 halves. That is larger than 1, so this geometric series converges. No, I said geometric. I meant p-series. Sorry, it's been a long day. This p-series converges. And then we have another example, final example. We have cube root of 4, cube root of 9, cube root of 16, and so forth. Cube root you can write with a power of 1/3. Starting with this term, this would be 9 to the 1/3. This one would actually be 2 to the 1/3. But it's easy to you really got to look at these sometimes under a careful lens. Like 9 to the 3rd. Well, I can write 9 as 3 squared, so that's 3 to the 2/3. 4 to the 3rd. 4 squared, I meant. 16 to the 3rd, you can write 16 as 4 squared, so that's 4 to the 2/3. 25 to the 3rd, that 25 is 5 squared, so that's 5 to the 2/3. Basically, you can see where it's possible to rewrite this as the counting values with a common power of 2/3. So over here, we can translate this series into the sum from 1 to infinity, 1 over n to the 2/3. Well, the power, our p-value, is 2/3. That's less than 1, so this is a divergent p-series.